The James Webb Space Telescope has just uncovered a cosmic phenomenon that defies imagination, a newborn star violently ejecting material, sculpting the foundation of an alien solar system. In a swirling, chaotic expanse of space, shockwaves ripple outward, igniting the birth of brand new worlds. Tune in, because what's happening now will shatter all we know about planet formation. At the heart of this cosmic drama lies HH30, a Herbig-Haro object nestled within the Taurus molecular cloud, about 450 light-years from Earth. It's a region teeming with gas and dust, and HH30 stands out as a particularly dynamic corner of this celestial nursery. Herbig-Haro objects, for those not well-versed in stellar lingo, are intense glowing spots that form when the energetic jets from a young star plow into the surrounding interstellar medium. The resulting collision produces shockwaves, and those shockwaves light up the gas, creating the dazzling display captured by Webb. But there's more to this cosmic story than meets the eye. This isn't just eye candy for astronomers. The detailed view provided by Webb offers valuable clues about the birth of solar systems. To understand the big picture, scientists have been piecing together data from various sources. Webb's infrared observations, combined with information from the Atacama Large Millimeter Submillimeter Array, ALMA, and the Hubble Space Telescope, paint a complex portrait of HH30's environment. They reveal layers of dust and gas moving in intricate patterns, hinting at the processes that might eventually lead to planet formation. One of the key findings is the behavior of the dust grains within the protoplanetary disk that surrounds HH30. These tiny particles, some just a fraction of a millimeter in size, don't simply sit still. They're in constant motion, migrating through the disk, clumping together, and forming denser regions. Over time, these dense clumps can grow larger, eventually coalescing into planetesimals, the building blocks of planets. This process isn't immediate. It unfolds over millions of years, but the seeds of future worlds are clearly visible in the data. Meanwhile, the radiation from the young star adds another layer of complexity. Intense starlight heats up the disk, causing some of the lighter materials to evaporate or sublimate. This process can strip the disk of certain volatile compounds, leaving behind a more concentrated mix of solids. Over time, these heated regions can migrate outward, creating temperature gradients that affect how materials clump together and what types of planets form in different parts of the disk. Adding to this dynamic environment is the gravitational pull of the star itself. The young protostar's gravity pulls on the gas and dust, causing them to spiral inward. This inward migration can create pressure fronts, where particles are slowed down and pile up. These pressure zones are crucial for planet formation, as they help concentrate the building blocks needed for larger structures. The balance of forces within the disk, jets, radiation, gravity, and gas dynamics, all contribute to the intricate dance that leads to planet formation. Another factor influencing the disk's evolution is magnetic fields. The young protostar generates magnetic fields that thread through the disk, affecting how particles move and how gas flows. These magnetic fields can twist and tangle, creating turbulence that mixes materials and helps redistribute angular momentum. The interplay between magnetic fields and the disk's rotation can lead to the formation of spiral arms, regions of enhanced density where particles are more likely to collide and stick together. These spiral features are often the precursors to planetesimals and eventually fully formed planets. Hubble's observations, on the other hand, contribute detailed visual and ultraviolet data. These observations reveal the fine structure of the jet outflows and the surrounding nebula. By comparing Hubble's images to Webb's infrared data, researchers can track the evolution of features over time. This ongoing monitoring allows astronomers to see how the environment changes as the young star matures and as the disk evolves. The combination of these different data sources creates a more complete picture of the processes at work, enabling scientists to build more accurate models of planetary system formation. Understanding the formation of solar systems is not just about observing the dust and gas. It's also about unraveling the chemical recipes that lead to the diversity of planetary compositions. The composition of the disk, what types of elements and compounds are present, plays a crucial role in determining what kinds of planets will form. Certain regions of the disk might be rich in water ice, while others may contain more silicates or metals. These compositional differences affect the types of planets that emerge, as well as their potential to host atmospheres, oceans, or even life. By studying the composition of HH30's disk, astronomers can compare it to the known properties of our own solar system. For example, they can look for signatures of water and organic compounds in the outer regions of the disk. These are the same types of materials that may have been delivered to Earth by comets and asteroids, contributing to the development of life. By identifying these compounds in HH30's disk, scientists can gain insights into how common these building blocks might be in other systems and whether the conditions that led to life on Earth are unique or widespread in the cosmos. As the study of HH30 continues, new technologies and methods are being developed to probe even deeper into the disk's structure. High-resolution spectroscopy, for example, allows astronomers to detect subtle shifts in the light coming from the disk. These shifts can reveal the velocity of particles, the presence of specific molecules, and the dynamics of the gas flows. By refining these techniques, researchers can uncover new details about the interactions between gas, dust, and jets. JWST keeps revealing new things, showing us more about how planets are made. Future missions and observatories may also contribute to the study of HH30 and similar systems. For instance, upcoming space telescopes equipped with advanced instruments could provide even sharper images and more precise measurements. These next-generation observatories will help fill in the gaps in our knowledge, allowing scientists to explore the earlier stages of planet formation in greater detail than ever before. In addition to direct observations, laboratory experiments and computer simulations play a crucial role in interpreting the data from HH30. Scientists use these tools to recreate the conditions found in protoplanetary disks, testing how particles interact under various pressures, temperatures, and magnetic fields. These controlled experiments help validate the models and theories developed from observational data, creating a more robust framework for understanding planet formation. As more discoveries are made, HH30 continues to stand out as a key system for studying the origins of solar systems. Its edge-on orientation, rich environment, and dynamic processes make it an ideal laboratory for exploring the physics and chemistry that drive planet formation. By piecing together the story of HH30, astronomers are not just learning about one distant star, they're uncovering the fundamental processes that shaped our own solar system and countless others throughout the universe. Each observation of HH30 brings new insights and raises new questions. What triggers the initial collapse of the disk's gas and dust into denser regions? How do the jets interact with the magnetic fields and turbulence to shape the disk's structure? What role do temperature gradients play in determining where different types of planets form? By pursuing these questions, scientists are building a more comprehensive understanding of how solar systems come into existence. In the grand scheme of the universe, HH30 is just one small corner of the cosmos, but its significance lies in what it represents, a window into the very beginnings of planet formation. It shows us that even in the vastness of space, the forces of nature work tirelessly to create new worlds. By studying this remarkable object, we gain a deeper appreciation for the intricate processes that have shaped our own solar system and continue to shape the universe around us. One of the telescope's standout features is its enormous segmented mirror, about 21 feet across, that acts like a giant light bucket. The more light you can collect, the clearer and more detailed the image. And JWST's massive golden mirror doesn't disappoint. Combine that with its cutting-edge instruments, like the near-infrared camera, NIR-CAM, and the mid-infrared instrument, MIRI. And you've got a cosmic powerhouse capable of detecting the faintest signs of nascent solar systems. What's especially intriguing about JWST's recent findings is that they provide a rare glimpse at how a solar system begins to assemble itself. In this case, it's zeroing in on a protoplanetary disk, a sprawling cloud of gas and dust that surrounds a newborn star. Think of it as the raw materials for making planets, moons, and other celestial bodies. Over millions of years, the tiny particles in this disk start sticking together, growing from microscopic specks into rocky planets and gas giants. For the first time, we're getting a front-row seat to these formative stages, watching the earliest pieces of a solar system click into place. But JWST isn't just taking pretty pictures. It's analyzing the chemical fingerprints of these young star systems, sniffing out the building blocks of life itself. In some cases, it's finding water vapor, organic molecules, and other elements critical to life as we know it. This discovery is a tantalizing hint that conditions ripe for life might not be confined to our own solar system. Imagine a future where we can trace back the ingredients for life in places hundreds of light years away, thanks to the data gathered today. The telescope also offers new insights into the dynamics of these protoplanetary disks. By observing how gas and dust interact, it's shedding light on how planets carve out their orbits, how they migrate closer or farther from their parent star, and how their final positions settle into the stable configurations we see in mature solar systems. In other words, it's giving scientists the tools to refine their models, making them more accurate than ever before. And while the telescope's data is a treasure trove for researchers, it also sparks a broader sense of wonder. The idea that we can look so far into space and see something that resembles the early days of our own solar system makes the vast, cold universe feel just a little more connected to us. It's a reminder that the stars we see twinkling above might host worlds in the making, each with its own potential story. Moreover, JWST's ongoing observations help refine our theories about how our own solar system formed. By comparing our home system to these emerging ones, we can see which processes are universal and which might be unique to our corner of the galaxy. This comparative study provides a broader context for understanding why Earth turned out the way it did. From its stable orbit to its life-sustaining conditions, it's a cosmic reflection, as if we're looking back in time to see the steps that led to the world we know today. Beyond simply observing these disks, JWST is helping researchers identify the chemistry of these alien systems. The telescope's instruments can pass the light from these regions to reveal the presence of specific molecules, like carbon dioxide, methane, and ammonia, that play a role in planetary formation. These chemical signatures act as a kind of recipe for how plants grow, and they can vary widely from one system to another. By cataloging these differences, scientists are gaining a clearer picture of the diversity of planetary systems in the galaxy. With every new find, Webb helps us understand more about how planets begin. Another compelling aspect of JWST's work is how it allows astronomers to test long-standing hypotheses about planet formation. For instance, one theory suggests that giant planets often form beyond a certain distance from their star, where icy materials can coalesce more easily. JWST's ability to observe these distant regions in unprecedented detail lets researchers verify whether this ice line truly influences where large planets appear. The findings so far suggest that our own solar system might not be so unique. Other systems appear to follow similar patterns, hinting at universal principles guiding the birth of planets. But the telescope's impact goes beyond confirming theories. It also reveals the unexpected. Sometimes the data show disks with unusual shapes or chemical compositions that defy traditional models. These anomalies push scientists to revisit their assumptions and come up with new explanations. In this way, JWST isn't just a window into the past, it's a catalyst for new ideas and discoveries that reshape our understanding of the universe's creative processes. As we gather more data, the emerging picture of these alien systems becomes richer and more detailed. We can start to identify trends, like how certain types of stars influence the structure of their disks, or how specific chemical conditions lead to the formation of rocky planets versus gas giants. This pattern recognition is crucial for building a comprehensive framework for understanding planet formation. Instead of isolated discoveries, we're now seeing how all the pieces fit together. The data JWST provides also offers insight into the timeline of planet formation. While planets might take millions of years to fully form, JWST's snapshots of systems at various stages help fill in the blanks. By comparing younger and older systems, we can estimate how long different steps in the process take. For example, if a particular type of molecule is abundant in a very young disk, but disappears in older ones, scientists can infer how quickly certain chemical reactions occur. This chronological understanding lets us create a more detailed story of how planets go from specks of dust to full-fledged worlds. Furthermore, the telescope's observations have a ripple effect on related fields of study. Understanding how planets form helps refine our search for habitable worlds. If we know which chemical conditions are linked to the emergence of life-friendly environments, we can target our searches more effectively. This connection between the formation of solar systems and the search for life is a powerful example of how JWST's discoveries overlap and amplify each other. The telescope's ability to observe distant regions in detail also helps us understand the environments where planets first take shape. Temperature, pressure, and radiation levels all play a role in determining what kinds of planets will form and where. JWST's detailed measurements of these conditions give us a clearer picture of the incubators where planets are born. This information not only enhances our understanding of the distant universe, but also provides valuable context for interpreting our own solar system's history. As the telescope continues its work, the discoveries are likely to come in waves. Each new finding builds on the previous ones, creating a cumulative body of knowledge that changes how we think about the universe. While JWST's primary mission is to observe the early universe, its ability to track the formation of planets and solar systems is turning out to be one of its most impactful contributions. It's showing us that the story of creation is ongoing, with new chapters being written in disks of gas and dust around young stars. This evolving narrative isn't just for scientists, it's for all of us. The more we learn about the universe's workings, the more we appreciate the delicate balance that makes life possible. JWST's discoveries remind us that they were part of a larger, interconnected cosmos. By studying these far-off systems, we gain perspective on our own place in the grand scheme of things. Looking ahead, the possibilities are exciting. As JWST continues to refine its observations, we can expect more detailed images, more chemical analyses, and more refined models of planet formation. These incremental steps will bring us closer to answering some of the biggest questions humanity has ever asked. And as we learn more about how solar systems form, we're not just filling in gaps in our knowledge, we're building a legacy of discovery that future generations will build upon. As JWST gathers more data, it opens a door to further exploration. The telescope's ability to study the composition of alien worlds and their atmospheres offers an unprecedented look into what makes a planet habitable or not. By examining the molecular structures and atmospheric layers of these distant worlds, we can start to piece together a checklist for habitability. This is more than just an academic exercise. It's a vital step toward finding environments that might one day support human life or other forms of life as yet unknown. Moreover, JWST's ability to peer into the early universe complements its planet-finding mission. By studying how the first stars and galaxies formed, scientists gain a better understanding of the conditions that led to the formation of the very first solar systems. This context is invaluable. It's like understanding the roots of a tree to better appreciate its branches and leaves. Knowing where it all began gives us a fuller picture of why planetary systems, including our own, formed the way they did. The telescope also has a knack for finding surprises. Beyond identifying new planets, it often stumbles upon phenomena that researchers hadn't anticipated. Unusual light patterns, unexpected chemical signatures, and structures that defy conventional models all provide fuel for new questions. These surprises aren't just interesting, they're the sparks that drive innovation in astrophysics. By challenging existing theories, JWST ensures that the scientific community remains flexible and ready to adapt to new information. As we uncover more about the birth of new worlds, can we be certain that other star systems might one day host life like ours? Let me know what you think in the comments, and don't forget to like and subscribe for more.